Hi everyone, welcome back to Chem Story. Now that we've already gone over how to name and draw alkenes, it's time to shift our focus and look at how they actually react. Before we dive into specific mechanisms or reagents, let's take a step back and get a big picture view of alkene reactivity. In this lesson, we'll look at why the double bond is so important, what makes it so reactive, and how that reactivity leads to all kinds of transformations. Once we get these core ideas down, the rest, all the detailed reactions, will make a lot more sense. Let's start with the double bond. That carbon-carbon double bond is what really defines an alkene. It's made up of two parts, a sigma bond and a pi bond. And here's what's interesting. The pi bond adds extra electron density above and below the plane of the molecule, and that makes the area around the double bond electron-rich. If you look at the electrostatic potential map, you'll actually see this. The red and orange areas, that's where the electron density is highest, and it's all focused right around that double bond. Now let's take a closer look at the pi bond. A pi bond is weaker than a sigma bond, so it breaks more easily. It forms from the sideways overlap of p orbitals, but that overlap happens farther from the nucleus, so the bonding isn't very strong. And because of that, when an electrophile shows up, the pi bond is usually the first to react. That's why we say it's more reactive. If we check the bond dissociation energy, a double bond takes about 611 kilojoules per mole to break. The sigma part is 347, and the pi part is just 264. That's why in most reactions, it's the pi bond that moves first. There's another reason the pi bond is more reactive. It's higher in energy than a sigma bond. If you look at the molecular orbital diagram, you'll see that the pi bonding orbital sits above the sigma bonding orbital. So it's easier to move or excite those electrons. And when electrons are already at a higher energy level, it doesn't take much to get them reacting. That's why the pi electrons usually move first when alkenes react. So here's the key idea. The pi bond is electron-rich, and that's why it can act as a nucleophile. In most reactions, the double bond breaks the pi bond and uses those electrons to form a new bond with an electrophile. Think of those pi electrons as a reactive lone pair, reaching out to attack anything electron-poor. That's how most alkene reactions begin, with the double bond making the first move. Now that we understand why the double bond is so reactive, let's talk about the types of reactions alkenes usually go through. And the most common one by far is the electrophilic addition reaction. So how does it work? Well, the double bond acts as a nucleophile. It donates electrons and attacks an electrophile, something like AB. When that happens, the pi bond breaks, and A and B get added across the two carbon atoms. A and B could be all kinds of things, a proton, a halide, or maybe a hydroxyl group. So what started as a flat double bond ends up as a single bond, with two new groups attached. There's another important type of reaction where alkenes form cyclic products, and this usually happens with either carbenes or parasites. In both cases, the double bond still acts as a nucleophile, but instead of adding two separate groups, it reacts with a single species and forms a three-membered ring in one step. With a carbene, the result is a cyclopropane ring, where both ends of the double bond connect to the carbene-carbon. And with a parasite, like MCPBA, the reaction gives you an epoxide, a three-membered ring with an oxygen atom. So keep this in mind. Not all alkene reactions lead to open-chain products. Now let's switch gears and talk about radical additions. They're not as common, but their mechanism is pretty unique. It's a chain reaction with three main steps: initiation, propagation, and termination. Unlike the usual electrophilic additions, this one starts with a halogen radical. That radical attacks the double bond, forming a carbon-centered radical. Then that carbon radical grabs a hydrogen, usually from something like HBr, and in doing so, it creates a new halogen radical to continue the chain. Now let's zoom out for a second. This slide gives us a nice visual summary of how alkenes can react. At the center is a basic alkene, and depending on what you add, you get very different products. You've got hydrogenation with H2 and a metal catalyst, halogen addition, acid-catalyzed hydration, hydroboration oxidation, and dihydroxylation. Some reactions give syn addition, some give anti, and others are stereospecific with clear three-dimensional outcomes. It's a great way to see just how versatile the carbon-carbon double bond really is. Finally, let's talk about oxidative cleavage. This isn't just a modification of the double bond. It completely breaks it. You start with an alkene and end up with two fragments containing carbonyl groups. Strong oxidizers like ozone or potassium permanganate do the job, cleaving the double bond and turning each carbon into something like an aldehyde, a ketone, or a carboxylic acid. So this isn't really an addition, it's a cleavage reaction, and it's super useful in structure analysis. Now let's take a quick look at the scheme. It shows a few examples of oxidative cleavage reactions. And here's the key point. After reacting with ozone, we get an ozonide intermediate. But what happens next depends on the reagent we use to treat that ozonide. If you use something like zinc, hydrogen peroxide, or sodium borohydride, you'll get different products depending on which one you choose. We'll break down the mechanism in more detail in a later lesson. Next, let's go over a few chemical terms that often come up when we talk about reactions of alkenes. First, let's clear up two terms that sound similar but mean very different things: selectivity and specificity. Selectivity means that a reaction favors one product over the others, but not completely. You still get a mixture, but one product clearly dominates. Like, if you get 80% of one isomer and 20% of another, that's selective. Specificity, on the other hand, means the reaction gives only one product. No side products, no mix. Just one, every single time. Now, in real life, most reactions are selective, not specific. But when you do get specificity, it's a really powerful tool in synthesis. Now let's talk about regioselectivity, which is all about where a new group adds when there's more than one possible spot. In alkene reactions, that usually means you could end up with constitutional isomers, same formula, but different structures. If one isomer forms more than the others, we say the reaction is regioselective. And this really matters when the alkene is unsymmetrical, like when one end of the double bond is more substituted than the other. A classic example of regioselectivity is Markovnikov's rule. Let's say you're adding HBr to an unsymmetrical alkene. According to the rule, the hydrogen goes to the less substituted carbon, and the bromine goes to the more substituted one. Why? Because that path gives you a more stable carbocation ion intermediate. So this rule isn't just something to memorize. It's based on how the mechanism works. There's also a broader version. The electrophile adds in a way that forms the most stable intermediate, and that's almost always tied to carbocation ion stability. Knowing this helps you predict the major product in most addition reactions. Here's a real example. When an unsymmetrical alkene reacts with HBr, you can get two possible products. In the Markovnikov product, the bromine ends up on the more substituted carbon. In the anti-Markovnikov product, it goes to the less substituted one. So what makes the difference? It all comes down to the reaction conditions. Without peroxides, you get the Markovnikov product. But if peroxides are present, the mechanism shifts, and the anti-Markovnikov product is favored. It's a great example of regioselectivity, and a reminder that understanding the mechanism is key to predicting the outcome. Now let's talk about stereoselectivity, which is all about how groups are arranged in space after a reaction. In alkene additions, we care not just about what adds, but how it adds, the three-dimensional outcome. And here's the key. The way the groups end up depends on two things: the reaction mechanism and the direction the electrophile approaches from. Sometimes, one stereoisomer forms more than the others, and when that happens, we call the reaction stereoselective. This explains why some products come out as cis or trans, or why certain reactions give specific chiral centers. One of the most common types of stereoselectivity shows up in syn and anti-addition. Here's the idea. In syn addition, both groups, A and B, add to the same face of the double bond. They come in together from the same side. In anti-addition, they come from opposite sides, one from the top, one from the bottom. These differences come down to how the reaction works, what kind of intermediate forms, and what its geometry allows. So depending on the mechanism, you can predict whether it's syn or anti. And that's what stereoselectivity is all about. We'll go into this more when we cover reactions like halogenation and hydroboration. Thanks for watching, and I'll see you in the next Chem Story video.